addresses the innovative pulsed current profile of resistant spot welding schedules for complex sheet combination in car body. I'd like to say a few words about my school here first. My school is located in the southern part of the South Korea, in here, the city name called Busan. And probably visualization of the school location can be more easily done by in conjunction with the other companies' locations. So we have nearby Nuno Samsung is in the same town, and also Ulsan, there's a Hyundai Automotive, and also far away we have GM in nearby Seoul, Hyundai Steel, Hyundai Automotive, and Kia Motors. And all of those companies, our laboratory are collaborating in this research field. So I'd like to express my appreciation on their continuous support, and these are some of the facilities we have in our laboratory. So what are the innovative pulsed current profiles, which I'm going to talk about today? Well, here's the motivation here. The body weight of the car body need to be required, and there are some new approaches for car design optimization, specifically more use of multi-layer sticks, various steel grades, and also various zinc coatings, galvanized, galvanized, press hardened steel with the zinc coating or aluminum silicon coating, and a lot of material thickness gauges and changes in stack orders. Because of these factors, based on the car body design, more difficulties arise in here. So here's the challenges and defects in resistant spot welding. You probably see a lot of heavy spatter during the manufacturing line, and also inadequate weld nugget formation, especially interfacial failure with the small nugget diameter, and also incomplete penetration, just Ansel Mittal introduced in previous speech. And also narrow weldable current range with the very high strength steels, and also large shrinkage cavity and poor surface qualities. So it requires the process validation and joint feasibility, and more advanced welding machine equipped with such as adaptive control is also required. And also optimization of welding parameters with finding the optimal welding current, welding force, and welding time. And lastly, they are looking for the use of pulsed current profile, which is also known as a multi-pulse schedule, as you can see from the image from the bottom here. So let's start with the definition. What's the pulsed current profiles in here? Well, let me start with the constant current profile, which is also known as a single pulse. There's a saying, providing approximately constant current and heat input without any cooling cycle. However, in case of pulsed current profile, which is also known as a multi-impulse, it actually providing an interrupted current heat input using the impulse mode with or without the cooling cycle. So actually the magnitude of the current can vary with each pulse. Some of the examples you can be seen in here. So I looked at there's some early studies using this pulsed current profiles. Year 2015, they have used this pulsed current profiles for the very high strength steels. They did the cross-current post-weld heat treatment, improved the mechanical performance of the nugget. I think they succeeded in achieving this goal. But in also year 2014, World Auto Steel suggested several different types of pulsed current profiles. So weld schedule with the pulsed current profiles for advanced high-strength steel can have weld current range similar to mild steel. So yeah, that is true. But I looked into some of the challenges in here, what we have now. Application of the post-pulse heat treatment pulse to improve the fracture mode of the resistant spot welded advanced high-strength steel, where it requires a very long welding time, sometimes more than 40, 50 cycles. And secondly, mostly developed for the similar two-seat combination. So cannot be used for dissimilar complex multi-seat combination like a 3T or 4T stack-ups. And also lack of guideline for easy use. So here, I looked at some of the needs from the automotive industry. They also wanted to have a fast and accurate decision-making for optimized welding condition for the current force and welding time for two-sheet, three-sheet, four-sheet, similar to similar combination. At the same time, they wanted to have optimized welding schedule, detailed guideline of using pulsed current profile. They want to know how to use this pulsed current profile with the high gauge ratio. And also they wanted to have a suggestion of detailed welding schedule with the field variables such as gap, adhesive, and also some sheet-to-sheet interfaces in adhesive. And lastly, they wanted to have a cost saving and of the RSW robustness and also improvement in welding quality and overall guarantee of the crash worthiness. So I think they wanted everything in here. So I looked at how they optimized their welding process or welding optimization schedule. They start with the feasibility test in welding lab for a given material combination in here. They check the nugget diameter or button diameter, also do the peel test, and also they come up with this welding window for each combination. And then they moved on to the robustness test in pilot plant. They check the gap control, spatter-free, continuous 100 weld, weld bond, and they come up with this welding condition sheet for this pilot plant. And then they threw this one into the quality control during the line building here. So they also adopt some of the offline programming, and they continuously update the welding condition for more optimized welding condition. However, throughout all of the optimization process, they were not quite sure what kind of welding pulse current profile they have to use. Do they have to use the single pulse, double pulse, or pre-pulse, or multi-pulse? So there was a kind of some of the challenges I had. So here's my objective of the development. Optimizing the welding parameters using the total heat input based calculation. So I tried to calculate the heat input required for each combination. And also investigate the mechanism of pulse current profile to improve the welding quality for the complex combination. And I'm going to introduce some of the case studies using the dispersed current profiles. So let me start with this total heat input calculation, what I did for any given combination. What you can do is, for any given combination with the similar combination, you can actually calculate the required total heat input for the target of a certain nugget diameter. At the same time, you can actually measure the heat input during the actual welding. So here's the heat input total to heat input total should be approximately similar in here. Here's my approaches. Step one. Let's define the 5 root T nugget diameter for a given combination. So 5 root T should be large enough nugget diameter for guaranteed welding quality. And then I calculate the heat input using the material database. I use the heat capacity, resistivity, thermal conductivity, strength, and hardness, and so on. I use about 9 or 10 material databases. And then I calculate the welding heat input to achieve the 5 root T nugget diameter for any given similar combination here. So I got a calculated total heat input in here. And move on to the step 2. From here, not the calculation. I do the actual test here. Conduct the actual weld which possess the 5 root T nugget diameter for a given combination. So I find the optimal welding parameters to have this 5 root T nugget diameter for a specific optimized welding current, force, and welding time. And then I measure the actual heat input during the resistance by welding here. So I do have a measured heat input in here. And then I adopt this calculated one and combine this measured heat input. And I do this is what I do. I calculate the total heat input, required total heat input for any given similar combination. Then I try to compare each other with the measured total heat input at the specific optimized welding current and time and electrical force. So if I have measured this total heat input, I can actually calculate back to what's the total heat input in calculation, which means actually I can calculate the nugget diameter as well. So these are my approaches, and another approach is what about the dissimilar combination? Where I do the this is something that I have to simplify. I cannot say everything, but in case of 2 different combination, I took some part of the heat from the one material, the other one from the other materials, and combined them and come up with the total heat input for the dissimilar combination. What about the dissimilar multi-sig combination? Same thing. Material 1, 2, 3, I take each required heat input and combine them into the one. And then I did the validation test. This is the welding current and welding time And this is dispersion current limit for this combination. And with this calculation, I come up with this welding current and welding time, which is right before the dispersion current and time. And the other case, it was also a very similar case. So it was validated. I want to emphasize this thing in here before I move on to the pulsed current profile in here. Well, there is actually differences in nugget growth mechanism between the mild steel and high-strength steel, which is also addressed by the answer meter. In case of mild steel, if you see the dynamic resistance behavior with welding time, dynamic resistance increase very slowly and then reach the maximum at the end of the welding time, which means that the nugget will grow very slowly until end of the time with a relatively large nugget diameter, larger than 5 root T. Here's the animation in here. So it starts with welding time, grow until end of the welding time. It grows into a relatively large nugget diameter. In case of high-strength steel, if you look at the dynamic resistance curve in here, actually with the very high initial contact resistance, and then the beta peak of the heat in here is heat generation is very quick here. So it actually heat generation very quick at the early welding time, and then no more growth of the welding nugget. Here's the animation for high-strength steel. Actually, you have a very fast nugget growth, but at the later, no more nugget growth here. That's why you have a lot of small nuggets in very high-strength steel. Obviously, if you use the very excessive high electro force, then you can increase further than in here, but this is the kind of limitation. If you grow this nugget very fast, what happens is that there will be, at each edge of the corona bone area, there will be sheet separation. So there's no any space you can grow the nugget in here. In case of three-sheet stack, resistance power welding three-sheet, four-sheet stack with a different in grade and thickness. This is same thing with the answer introduced. A very thin mild steel, 0.7 millimeter, high-strength steels. So mostly heat will be generated by this high-strength steel side, and this is what happened in here. Here, most of the heat, and not able to reach the enough heat to melt the thin mild steel sides. But answer meter showed the quite good promise for the good joining strength. However, in here, I'd like to emphasize one more thing. The nugget growth rate with the time is quite different between the mild steel and high-strength steel. So poor heat balance with welding time in high-strength steels. And also, in case of a three-sheet and four-sheet stack combination, poor heat balance through the thickness. So what we have now in actual field manufacturing line, we have a poor heat balance with welding time, poor heat balance with welding thickness. So how can we improve our welding quality or change this condition with using the pulsed current profiles in here? Here's my case studies. Pulsed current profile optimization for two-sheet similar combination, especially for the advanced high-strength steel. Well, with any of the combination, what I can actually calculate the required total heat input, or anyway measure the required total heat input by the welding. However, if I want to use the pulsed current profile, here's my headache. How can we divide into the pulsed current profile? Should we divide this total heat input into the 2 heat input or 3 heat input? Or should we put the high heat input at the beginning early, and less heat input later? Or do we need to have a very small heat input at the beginning with a very small current, or in the later larger current, high heat input? What about the trippers? So what's the deal here? This is some of the things we need to kind of figure out. What are the mechanisms of working in here? So I start with looking at the effect of initial first, the first in here. What I notice is that, as you can see from here, from the previous slide, in case of advanced high-strength steel, the nugget growth is very fast, which means that you need to have a very good large contact area before you enlarge grow the nugget. So what we need is we need to have a large interface contact area without having extensive nugget growth for the press hardened steels or any high strength steel. So I traded two conditions: high current with the short welding time, low current with the long welding time. So here's the high-speed movie, which I going to show you in here. In case of high current and short welding time, what happens is that you actually generate the heat in interface very quickly. And we were able to achieve the large interface contact area, which means that because of this high peak current, you actually minimize the contact resistance very quickly. But in case of a low current with a long welding time, see what happened in here compared to the high current. You can see it in here. Yes, now it's starting. Low current, the contact area between the fang surface is increasing, but not as much as the extent of this high current case. So I captured the image between the high current and low current. You can see the difference very clearly. In case of high current short welding time, you will have a large contact area which can be used to grow the very large nugget in high strength steels. So this is some of our research in here. There's some difficulties to obtain the large nugget diameter resistance for welding for high strength steels. So in single purse, you can actually have about maximum 6 millimeter nugget diameter with 6 millimeter electrode tip. But we used this multi-purse, 3-purse, with a high current pre-purse and intermediate purse and main purse current. We were actually get the nugget diameter of up to the 7.24 millimeter with using the 6 millimeter electrode tip diameter. So this is the animation. You have a large contact area. Intermediate welding, you kind of stabilize this contact area. Now in main purse, you can grow the total nugget, actual nugget very quickly. So this is how we get the 7.24 millimeter of nugget diameter for, this is I think 1.2 gigapascal high strength steels. So here's another case study too. Pulse current profile optimization for high gauge ratio combination, 4-sheet, 3-sheet high strength steel with a very mild steel. As ArcelorMittal explained, it says yes, they are right. In case of mild steel, it has a very low resistance. In case of high strength steel, they have a high resistance, which means that in mild steel, because of they have a low resistance, they need a high current. But this high current will be very detrimental for this high strength steels. It will make the instant splash in here. So here's you can see in here, there is a confliction between mild steel. It requires the high current, but in case of high strength steel, it doesn't need a high current. So how do we deal with this case? What we found is that in mild steel, we still need a high current. Then let's put the high current in a very short time at the beginning. Then probably mild steel will have some heat generation, even though it will cool down with the temperature will conducted out through the electrode, but still they will have it. Here's our result. In single purse, as you expected, a lot of heat generation concentrated on the high strength steel side, but in case of pre-purse, you see there is a heat generation actually occurred at the mild steel side with the very high current pre-purse. So this is with the nugget diameter in here, it was improved about, compared to the single purse, with this pre-purse schedule, purse current profile, we improved about 57% of the nugget diameter. So I want you to look at this, we wanted to validate how this is working through the simulation in here. I want you to look at focus on in the top sheet in here, heat generation with the pre-purse current. Here's our simulation. You can see it here, yes, during the pre-purse schedule, there's a large heat generation at the thin side. But in case of a main purse, a single purse, the heat is growing, nugget is growing, but it probably stops in here. So there's a large difference has been validated through the simulation. With all of these pre-purse schedule, multi-purse schedule, there's one OEM wanted to test this result. And this is their production line condition before. And this is we provide them with the optimal welding pulse current profile with the 3-purse, 2-purse based on their our given material gauge and grade. So this is how they are doing the welding. You can see it from here, very large spatter is happening in here. Another large spatter, and then another large spatter, and it's probably have some sound with a very weird sound in here, but they are suffering from the large spatter with this production condition. And we provide them our optimum welding condition first current profile, and this is what we got. Not much spatter here, but you can see some of the smoke in here. No spatter. One spatter was in here, but no spatter, but a lot of smoke. So I think the manufacturing line was almost spatter-free. And then they actually checked the destructive test in here. It was all button failure, so it was very successful. In case of, we do use the, OEM use a lot of adhesive nowadays for the very crashworthiness. Here's what we have in here. In case of without adhesive, well, actually, it's the same thing. You have a heat generation in here at the early. In case of adhesive at the interface 1 in the mild steel side, well, this adhesive actually working as a heat generation source. So you don't need probably preppers, but there's a splash on this high strength side. And if you have adhesive in this high strength side, interface 2, you will have a very excessive spatter in here. In case of interface 1 and 2, same thing. So this is what I proposed, preppers. Yes, we were able to get the good welds. In case of adhesive in the interface 1, since we have a heat generation source by the adhesive, we don't need this high current pulse. So we need to reduce down this current in here. In case of this case, where we need to move on to the 3-pulse schedule. You need to down small current, short time, and then you need the heat in mild steel. That's why you need another current in here. This case is the same with this one. Large gap. Probably a lot of OEMs and tier 1, tier 2 companies are suffering from these gap problems. So what happens is that if you have a gap, then large spatter, it ends up with a very large cavity in here. So we tested it with a 4mm gap, and so quite large spatter cavity. And then we tested the tensile shear strength. It was only like close to 10 kilonewton with a normal welding schedule. And then here's the tip. When you have a gap, please use the upslope. If you use the upslope, we were able to get about double the tensile shear strength. And then we checked the actual failure type, and it was without upslope, there's a lot of cavity. With upslope, button failure, and very limited, very small cavities. In case of 5mm gap, same thing. We used upslope. We are not able to tell you exact schedule in here, but upslope works in here. Probably next talk is about the liquid metal enrichment. I also had some of the experience with the liquid metal enrichment here. The automotive and steel companies are suffering from also a lot of cracks after the resistance for welding in here, especially for the Gen 3 steels. And this is the video I took about 4 years ago. There's a lot of LME cracks actually happening during the resistance for welding. Then this is another first current profile which I applied it. But we still have we need to keep the nugget less than critical nugget diameter of the LME. So here's the further development here. We had everything in, try to reveal some of the mechanism and make some calculation, but still automotive company didn't quite satisfied with using this kind of algorithm. So we did the user-friendly interface with the welding schedule optimization. So we come up with the automatic total heat input calculation based on the given sheet combination, and as an engineering solution, we predict the optimum pulsed current profile as well as the nugget diameter and tensile shear strength. And this is the three sheet combination I'm going to here. I have in here we have about 8 or 9 OEMs material database in here. So this is how it works. You select the database of the OEMs and use the tip diameter, select the 6-8 tip diameter, any of the constant current adaptive control, 3-sheet, 4-sheet combination, choose the materials and choose the thicknesses, And also, you can choose the single pulse, pre-pulse, multi-pulse, and then analyze it. It will come with the optimum welding parameter with the nugget diameter. And then you can also choose the adhesive, and it actually changes the welding parameters, as you can see here. Another engineering solution with this one, digital manufacturing. Engineering solution with the combining welding parameter predicting and offline programming to achieve the reduction in development time and improvement in welding quality. So we actually implemented our mechanism into this offline programming program. So what they can do is they can actually import the previous welding parameter for a given part sheet combination for a specific robot, and actually part cross-section in here information can be imported, or we can actually manually input them. And then what we can do is we can compare between previous welding parameter which was used at, and then also compare with the suggested welding parameter, and then we kind of make some of the ranking numbers. And then finally, we can upload the new updated welding parameter into the welding controller, which means welding machine. So it can save a lot of times for the development stages. So here's my summary. I think the time is up. It's all about the heat balance using pulse current profiles. So I'd like to say heat balance with time. Let's grow the nugget very slowly, and also heat balance through the thickness. We can achieve these goals with using the pulse current profiles. I'd like to acknowledge my former students and current students, Dr. Chang-Wook Ji, Siva Prasad, Jae-Won Kim, Aseo Junman, Tae-Young Kang. They did all of this work and development, and I only do the talk, I think. And thank you for the attention, and looking for the collaboration opportunities. Thank you very much.